All right. Hello, everyone. My name is Zoe Dietrich, and I'm going to be talking a little bit about climate change below the surface of the ocean. I'm really excited to be chatting with you all today, and I'm sad that we can't do it on a live Zoom, but hopefully this will do. And so I'll start by just telling you a little bit about me. So I graduated from MAYhem in 2017, and I go to a small college in Maine now called Bowdain College. I'm an earth and ocean science and biochemistry double major, and I love ocean science and specifically those little single-celled organisms that facilitate all of these different cycles and transformations in the ocean. And so you can see on the right there a photo of me photobombing Hank and Tony at Science Olympiad in 2015 when Tony decided it was a good idea to bring a fake trophy to make it look like we won. So there you go. All right, so I have some goals for us today. And the first one is to take some things that we already know, and then from there to figure out two of the most fundamental systems in the global ocean. After that, I want us to understand how these systems are absorbing about 25% of our annual CO2 emissions. And so it turns out the ocean is helping us a lot, and we're going to go through exactly how that works. And thirdly, I want us to just think a little bit about how these systems might change as climate continues to warm and what impact that might have. But overall, I really just want you to see that ocean science is this beautiful blend of biology, chemistry, and physics. It's like a big swirled up ice cream cone. And so I've created these chemistry, physics, and biology stamps that I'm going to put on each slide as we cover concepts related to those fields. All right. So I'd like us to start with something that hopefully all of us are a little bit familiar with, and that is this concept of density. So I say density, and this is probably what comes to mind. Density equals mass over volume. All right, so we have this density metric, and I want us to think about this in terms of water. And so if I put up this box of water, let's say this is a box of fresh water, and the density is 1 gram per mil, mass over volume. We know this, the density of water is 1. All right, now let's take this box of water, let's move it over here, and then let's put some salt in it. So I just dissolved some salt in there, and now there's some sodium ions and some chloride ions. And those are gonna make the mass of this box increase. And if you look up at this equation, if you increase the mass, you're gonna increase density too. And so now let's say our new density is about 1.023 grams per mil. Okay. Now, let's take this salty box of water, let's move it over here, and let's cool it down. So we're making this cold. When you think about it, when we make things cold, they contract, right? And so if we contract this box of water, we're gonna lower its volume. And that, if we lower the volume, it's gonna make our density go up because of the way of this inverse relationship. So density goes up. Let's see if I can move myself, there we go. All right, and let's say this new density is about, oh no, I have to move this back down. Nope. Oh, there we go. Okay, it's about 1.029 grams per mil, and that's an average density of seawater. Okay, so, oh geez. There we go, okay. So I'm gonna put chem and physics stamps on these because this is really chemistry and physics, and you might have learned about it in both classes. All right, so moving on, the density of water is not always 1. That was a shocker that I'm pretty sure I learned in college. And I'd just like us to remember that dense things are going to sink because they have more mass per volume versus less dense things are going to rise. So we've probably seen this before. It's just a layer of water with a layer of oil above it. And so the oil is less dense. And so it sits on top of the water, which is more dense. See if I can move myself again. Oh no, okay. And if we put some water in here, it would sink and get down to where the water is because it's more dense than oil. Okay, so now that we understand this density concept, we can think about this thing called convection. So let's start with this tub. Here's a tub, and on the left, it's hot, and on the right, it's cold. Okay, so now we're gonna put our box of water in this tub. There it is, there's our box of water. And it's right by this cold thing. Okay, so it's gonna get cold. It gets cold, it's shivering. And what we just learned is that when things get cold, they become more dense, right? When things become more dense, they sink. So it's cold, it's dense, and it sinks. And it hits the bottom of this tub, and it just keeps going, and it goes around here, all right? And then it hits the side of the tub, and it goes up because it hits the side of the tub. And now it's at the surface, and it's next to this hot thing. So it heats up, and it's happy. And then where else does it go? It only has one other direction it can go. So it goes this way, and it gets really hot. Then eventually it goes over here, and it gets cold again. And we repeat the whole cycle, and this is physics. Okay, so now I want you to understand that this is exactly what happens in the ocean. Think about this tub is filled with water. This is the ocean. Here's the surface on top. Here's the deep part. It's about 4,000 meters deep. And in the ocean, instead of having some heater on the left, or on the left, we have the equator. So it's hot, there's a lot of sun, 0 degrees north. And instead of having a cooler, we have the Arctic. And so it's cold, it's 90 degrees north. And this is pretty much exactly what happens in the ocean as we just learned about it. Except in the ocean, it's just a little bit more complicated because there are continents, essentially. And so, but you can see what I was just talking about, and this is a map of this process we call meridional overturn circulation, which is the first big process I wanted us to uncover. And so you can see, if you think about the right-hand side of the box, that's what's going on over here. And so you have your hot water coming along, gets up here to the pole, it cools, and so it becomes more dense, and so it sinks, it goes down here, and then it's at the bottom. But it hasn't really hit anything yet. And so it's going along the bottom, it's going along the bottom, it's going along the bottom, 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 bottom. And then we come up here and we hit this continent, right? So we come up back to the surface like we saw on the left-hand side of the box. And then we move this way. First, if we're on the bottom over here, we're going along the bottom, come over to this side, going along the bottom. Then up here, we finally hit the continent, come up because we hit the continent on the left side of the box. And now we're at the surface again and we're warming up and we go around this big loop. We call it meridional overturn circulation, but it's just driven by density. Okay, so now we have one fundamental system down. Now we're going to go on to number 2. Okay, so I want us to think about another box of water, but it's bigger this time. So here's our box of water. This is the surface. Here's the sun. And this is the bottom. You can see some sediment on the bottom there. It's 4,000 meters deep. Okay, and what do we have living in our ocean? We have these tiny single-celled organisms called phytoplankton. You might have heard of phytoplankton before. They look like this, but they're too small to see. You'd have to have a microscope to be able to see them. Okay, so now we're going to do a little aside about some biology because we just put some biology into this physics and chemistry system. Okay, so I'm going to put kind of a nasty equation up here, but don't worry, we're going to make it through it. Okay, so here's an equation. This is just photosynthesis. So basically what's happening here, and all plants do this, trees do it, grass does it, turns out phytoplankton do it, is they take in carbon dioxide and water, and they use some energy from the sun, and they put out glucose, which is just this form of sugar. It's basically just them storing carbon into their cells, into their bodies, and they produce oxygen. And so, like I said, trees do it, grass does it, phytoplankton do it. And so all I want you to think about is that they're taking in carbon dioxide and they're putting out oxygen. And so what's wrong with this? We're putting in 1 C and 2 O's, but we're only getting out 2 O's. So the carbon is stored in the cells. It's stored in the bodies of these phytoplankton. So if we go back here, all I want you to think about is that these phytoplankton are just little bits of carbon that are doing photosynthesis. And so they're just little bits of carbon and they're living. And so what's going to happen eventually is they're going to die. And when they die, gravity is going to take hold and they sink down into the ocean. They sink and they basically just bring these little bits of carbon that are their bodies down into the deep ocean. So now we have to have another quick biology aside because it turns out that there's an opposite process to photosynthesis. This opposite process is called cellular respiration, but it's basically just breathing. And so you're using up some carbon that you have in this form of sugar called glucose, and you're using up oxygen, and you're producing carbon dioxide, water, and this molecule called ATP that we're not going to worry about. And so you have to think about, this is breathing. We do it, all animals do it. What's going to be breathing in the deep ocean? Well, it turns out there are these other single-celled organisms, bacteria, that live in the deep ocean, and these guys are just decomposers. They eat dead things, and they breathe. So basically, they're taking in oxygen that's just in the water, in the deep ocean, and they're eating phytoplankton. So they're taking in the carbon that's in these phytoplankton, and that is their source of this glucose, this sugar. And then they're outputting CO2. So basically, they're taking this carbon that was once in the phytoplankton and they're turning it back into carbon dioxide. They're doing the opposite process. And so if we go back here to this diagram, we can think about cellular respiration is happening at depth. Here's our bacteria. They are eating phytoplankton and turning the carbon inside the phytoplankton back into carbon dioxide. But every once in a while, you have a little phytoplankton body that makes it through and lands on the bottom. And so that carbon is exported to the bottom of the ocean, and it, eventually becomes rock over many, 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 many years. But what we care more about is this carbon that's turned back into CO2. And so I just want to make sure we're all on the same page. We're going to go through where the carbon is to understand how this is happening. So we start out with CO2 in the atmosphere. And phytoplankton take up that CO2 through photosynthesis, and they produce oxygen, and they store that carbon that was in the CO2 into their bodies. So now you have the carbon that's in your phytoplankton. And then two things can happen to the phytoplankton carbon. The first is that a tiny bit of it gets moved and falls all the way down to the bottom of the ocean, and that we call it export. And another form of export is when bacteria decompose this phytoplankton and turn their carbon into carbon dioxide. So then we have this carbon dioxide in the deep ocean. We have to think about, where does that go? Well, I have to say, this is called the biological pump. That is the specific term for this whole process we just learned about. So that's fundamental process number 2. Okay, thinking about where this CO2 goes, well, we have to go back here to the physics and chemistry. And so if you think about it, all throughout the surface here, this carbon, and we call it, it's carbon being exported. It's going from carbon in CO2 in the atmosphere into phytoplankton, and then into CO2 at depth or down to the bottom of the ocean. So it's being taken out of the atmosphere and brought to the bottom of the ocean. And so we can think about phytoplankton falling all throughout this ocean here. And then that CO2 gets looped into this bottom current that you can see my mouse following. It's going along the deep ocean. It's going, it's going, it's going, it's going, it's going. So it's being stored in the deep ocean, moving along this conveyor belt. And it's only going to come up to the surface when it hits one of these 2 points. So this is, remember that left side of the box, when the deep water hit the wall and came up to the surface. That's what's happening when this deep water hits the continent. And so that's when you're going to have all the CO2 that's accumulating in the deep ocean eventually get released back into the atmosphere. But luckily, the circulation process takes 1,000 years. And so all of the CO2 that we're putting in there is going to be in there for a while. But eventually this will happen and it will come back up to the surface. So that's how our ocean is taking up 25% of our annual CO2 emissions and storing it for about 1,000 years, which is pretty cool. And the ocean is helping us out a lot. But we also want to think about how these processes are changing. So remember this, I've been talking about this whole time, this convection process. And it turns out that it has a lot to do with the Arctic. So we're going to go up to the Arctic for a second. And here's our box of water again. So at this time we have some ice over it. So when ice freezes, it forms this crystal lattice structure, and this is chemistry. And there's no room in there for sodium and chloride ions. And so what ends up happening is that all of this ice is fresh. It's fresh water. So where does all of that salt go when this water freezes, but only fresh stuff can freeze? Well, all of the salt just goes into the water below it. And so if we think about it, this water is becoming salty as ice forms above it, and it's becoming cold because it's in the pole and it's cold up there. So remember this, if it's becoming salty and it's becoming cold, it's becoming more dense. And this is why that water sinks at the pole and starts that whole process of circulation. But if we think about what's happening in the Arctic right now, the Arctic is warming, and there's actually less and less ice formation each year. And so if you have to think about if there's less ice formation, you're going to have less salt being put into this water below. And if it's warmer, your water is going to be warmer. And so if your water is warmer and fresher, it's going to be less dense. And this is a big deal because its density is what causes the water to sink in the first place. So if the water is less dense, it's going to sink slower, and this whole loop will be slower too. And so this is a problem that scientists are actively studying right now, is that this global ocean circulation might slow down. And we don't know what impact that's going to have on weather, what impact it's going to have on currents or anything like that. And so it's a big problem people are trying to figure out right now. But we have to think about the flip side of this, which is that if you have less ice in the Arctic, you have more sunlight reaching the water. And if it's warmer, that creates more conducive conditions for life. And so basically, an ice-free and warmer Arctic Ocean means more phytoplankton. And it's true that we're seeing phytoplankton blooms happening earlier, happening longer. There's more phytoplankton, and this essentially means more carbon export, like we talked about before, and more carbon removal from the atmosphere. And so the point I'm trying to make is that there are these positive and negative impacts of climate change, and there are so many interconnected systems in the ocean, and we need biology and physics and chemistry to understand them all and how they all interact. And it's an exciting problem we have right now, is to look at how all of these systems are going to change and interact as our climate is warming. And so I guess my point is, we need your help if you're interested. It's just a really interesting, fascinating field to be in right now. And so I just want to move through and go through our goals one more time. So one of our goals was to figure out two fundamental systems in the global ocean based on things we already know, density. And we did this: meridional overturn circulation, that big diagram I showed you, and the biological pump, when phytoplankton take up carbon and move it to the deep ocean. I want us to understand how these systems are absorbing 25% of our CO2 emissions, and I think we do. It's because of the plankton. And then I hope you have a little bit of a sense of how these processes might change as climate warms and how interconnected all of these things are in the ocean. And so, yep, I'll check off all these things. Okay, and then, yeah, I hope that you understand that ocean science is just a big ice cream cone of everything swirled together. That's how I think about it. So if you have any questions, I think you're supposed to send them to Annika and Hank, although I'm not entirely sure. Look out for instructions on that. But feel free to reach out to me literally anytime. I put my email up here about anything, about ocean science, research, small colleges, Maine. Yeah. Okay, great talking to you. I'm going to stop sharing and end this meeting. All right.